We're going to be talking about monitoring. We actually left the tracing part out just because, I mean, with just half an hour, there's so much stuff to cover. But by all means, catch up with us, ask us questions. Yeah, here's the pointer. So we're basically dividing this presentation in 3 parts. I'll cover the first 2, and Tomek will cover the last one, which is, first of all, let's start with the basics. So your first look at a Scylla cluster, what people are usually looking at, and what are the drawbacks of the standard ways people have been monitoring stuff when applied to Scylla. Then how we actually structure our monitoring infrastructure, and then Thomas will explain to you more about what the individual metrics really mean. So when you deploy something new, I mean, the first instinct that most people have, or it's like take a look at Linux tools that are available in your CentOS, Ubuntu, whatever installation. Examples of such tools are things like top. Like, so you just deployed your cluster, and you want to know, am I maxing out the CPU? Or iostat, or netstat, you have a wide variety of them. They have limitations, and the first limitation is that they're only telling you a story about a node. They're not telling you a story about your cluster. So they're interesting, they're not useless. They're interesting for you to understand, okay, maybe I have an issue with this node, or my workload is causing the nodes to max out. We're going to look into that. But the most pressing problem, though, is that due to our architecture, those tools usually do not tell the whole story. Now, for you to understand that, let's look at a very simple example, top. Top really is, I mean, from what I hear from people trying it out and running those workloads, first thing most people run, if you just want a quick pick at the system, is, okay, my CPU usage. So top's going to tell you that. The problem is that unlike other software out there, we use a polling architecture, which is not a very common thing for you to do. So most people are not actually aware of that. But Scylla will very likely be using 100% of your CPU. And the reason it happens is that, as you can see it in here, when your request finishes executing, we will keep just busy waiting for a while, just because this way it can provide you with a better latency if a request happens to arrive right here. And only after this poll period, the CPU will be idle. Now, if you're not running at 100% CPU, then you are for sure underutilizing your CPU. So that's why top is actually still useful even then, because if I look at a CPU, and if I see like one of the problems we recently detected, Yao actually mentioned that, is that one of the CPUs was at 100% and the others were very close to 0. So that means probably schema imbalance. One of the nodes, one of the shards is not getting any requests. However, if we're running at 100% CPU, you cannot infer anything from this situation. Really nothing. Not even that you have moderate load. Reason being, you can have very small requests, and every time the poll period is about to end, a new request comes in. So in a situation like that, you're actually not using your cluster at all. It's very light load, and yet your CPU is at 100%. Some tools are actually quite useful. So iostat is an example. By the way, we will, of course, tell you more later about if top is not the answer, what is, when I talk about the monitoring infrastructure. Now, iostat is actually a quite useful one. I doubt you can all read the numbers. The numbers don't really matter. I mean, you have 92.90 here. It doesn't really matter. What matters is that iostat will tell you the load in the disk. There are better metrics in Scylla, so even that is limited. You should be looking at the IO scheduler. Thomas will talk about it in more detail, but we do have an IO scheduler that allows you to see what not only my disk is being utilized, but my disk is being utilized by compactions, by memtables, by memtable writes, by queries. But iostat really can be useful if you look at three things in particular, so the first thing, no, go back. The first thing you can look at is just bandwidth. So I mean, this is just for you to understand that it's not that the Linux tools are not there for nothing. I mean, you can look at the bandwidth of the disk. You can look at the utilization at the disk. So if you start seeing, for example, your service time going up, okay, maybe I need better disks, or we may have a problem in the IO scheduler because we're supposed to try to keep this low, but this still tells you something about your system. And even though I haven't seen it happen in real life, but maybe you have imbalance here, maybe your RAID controller is at fault. And so those kind of issues, I mean, are issues that you can see with Linux tools. Other thing to keep in mind, not all problems are actually database problems. And this example actually comes from the graph Avi used in his presentation. This is a real example, by the way. So what the red line that you see here is a tool called JHiccup that we're using to generate those metrics. And what this tool does is it tries to look into the JVM. So this comes from the client. The JVM here is the Cassandra stress tool. That is a Java tool. And the tool also has issues with garbage collection and waiting times and hiccups in general for several other reasons. So as you can see, a lot of our latencies actually correlate with the JHiccup latencies. So this is more of a parenthesis saying if you're monitoring your system, just remember, try to keep your client, your loaders into account as well. Some of our latency here is our fault, as you can see, so it's growing because we're having other stuff going on, but some of them really are the client's fault. So you're never going to get rid of those latencies just by tuning the database. You need to be aware of them. Okay, so if the standard tools that are available in Linux do not tell you the whole story, if they are not, if they're not all that you need, what else is in there? And it's collectd. So the answer for this is collectd. We export everything under the sun that we can. Well, actually, we try not to export too much because then you may get lost on them. But we do export a fair amount of metrics about the system. And those are the metrics that not only they are available for you to understand your cluster, they're also exporting information that we use, as Avi said, for workload conditioning. So things like, okay, am my compactions getting crazy? But I mean, they're available for you to see as well. So the components of the system, it's Scylla, the database itself, and an agent that I will detail shortly. All of that is exported to Prometheus, and it's available like Grafana that gets a browser interface. Now, taking a closer look at the agent, you can see that there is collectd that's basically monitoring the host, so the disk activity and the metrics that the Linux host itself exports. They are bundled together with the Scylla metrics and then go through collectd exporter to Prometheus. So when you reach, I'll just go back here a second. When you reach this stage, you actually have both host and Scylla metrics. So how do I look into it? So the first thing is that if you already monitor your systems with collectd, there is a reason why we're using collectd, because it's widely available. A lot of people already use it, so if you already have your monitoring infrastructure, by all means, you can just integrate Scylla into your metrics. There is no harm on it. There is a tool called ScyllaTop that I'll talk about it, and then Prometheus and Grafana, which are our major method of looking into Scylla. Now, ScyllaTop is more of an ad hoc tool. It's a top-like interface. It does have a very high resolution because tools like Prometheus, Grafana, they usually have a scrape period. They're not polling all the time. With ScyllaTop, you can have like a more detailed look into like every iteration of the counters. But they're really just good for ad hoc probing. I mean, okay, this is an example when I'm looking at the load. So this is called reactor load, which shows you the CPU utilization. So this is what we really should be doing instead of looking at top. So, right, so top will tell you CPU utilization as seen by the host. Very likely will always be 100%. And then looking at reactor load, you can actually see, so, okay, this is at 84%, so close to max out, but still room for more requests. You can see all the metrics available through our REST API, and ScyllaTop will list them as well. This is just for you to see as an example. ScyllaTop-L will list the metrics. I have a Scylla server here running with SMP1, meaning I just have one core. Those metrics are replicated core by core. And I have 145 metrics. So literally, we have hundreds of metrics about what's going on inside Scylla. Prometheus and Grafana really is the preferred method, the default way for you to look into the cluster. They will give you a nice progress view about what's going on over time. You can compose metrics, you can correlate metrics, you can look at them and get a much better view of what's going on into the system. Only drawback is a little bit harder to set up, but of course, to tackle this, we provide images. So you can look at Scylla Grafana monitoring GitHub. Not only you have the scripts to load Docker images from it, but you also have standard dashboards, the dashboards with the metrics we believe to be of importance. Of course, not all of the metrics we believe to be of importance, but a nice summary of them. So if you just fire Scylla Grafana monitoring, you will be seeing something like this. So you can look here at the total requests served. You can look at how your requests are being divided. So those are, I guess, right. Yeah, it's impossible even for me to see, but you'll see when you download it. The ones I remember by heart, those are requests per server, and this is the CPU utilization per server, but you really have all sorts of metrics in this dashboards. And as I said, this is the same graph Avi used in his presentation. We're trying to see which graph is the one that will be used the most by all of us. This one seems to be the clear winner by now. And it's nice for you to correlate the metrics, right? Even the client-side metrics can be put into the Grafana dashboard as well. And then you can see, okay, so I can really see here that if I have this spike down here, it is caused, this spike here is very likely caused by this. And I have my cache, and then I have a hiccup, a small hiccup here, correlates with this as well. So this is a nice interface for you to put everything together. Now, the real question is, what are those metrics? And I'll leave that to Thomas. We'll introduce you to the metrics themselves.
All right. So as Glauber mentioned, Scylla is exporting metrics to collectd. So let's look how collectd metric identifiers look like. There are several standard components, like the host part identifies metrics coming from given host. There is the plugin part, which usually maps to name of some component of the system, like a SQL server, for example. There's plugin instance, which differentiates between different instances of components running on the same host. There is metric type, and finally, type instance, which holds a metric name. Below you can see an example. This is identifier is for reactor load metric for shard 0 on node 1, and it's of gauge type. And Scylla is using shared nothing thread core architecture, so many components are sharded with instances per shard. So on running a single node, Scylla, even if you run single node, you will see multiple metrics coming from the same component, like in this example. Metric types can be grouped into two categories, gauge and derive. Gauge metrics are those for which value is presented as is by presentation layers like Grafana or Riemann dashboards. And derived metrics, for those, what's important is change over time. So instead of raw value, we present change of the value divided by time distance between samples. So for example, throughput metrics like number of requests per second will be implemented as derived metrics where we will have an underlying counter incremented on every request coming into the system. Then the presentation layer would calculate rate based on that. When metrics are exported to Prometheus, the syntax of the identifier is a little bit different. but it pretty much contains same elements. This diagram shows metric plugins which Scylla exports. Those are not all plugins, but pretty much the most important ones. You can see that we have plugins for major components and on different levels. We have, for example, a plugin for SQL Server metrics on coordinator side. You can have also plugin for replica side services, and then lower level components like commit log, mem tables, cache, and so on. There are also plugins for sister parts like reactor IOQs. Right, so let's look a bit at what kind of metrics actually are exported by Scylla. We have throughput metrics. For example, transport requests served. Those count the number of SQL requests which arrive at the coordinator. And we have database total reads and total writes. Those are counting replica side requests. You can use them to monitor the throughput of your server, as well as detect situations where there is an imbalance between nodes in the cluster. There are also error metrics. Notably, storage proxy, read timeouts, and write timeouts. Those count timeouting requests on the coordinator side. When you see them, you should probably drill down into the cause of those timeouts, like looking at if the server is not overloaded or checking for errors in the logs. Glauber already mentioned it. The best way to look at CPU utilization is by looking at reactor load metric. It's a percentage of time which Scylla spends actually executing work and not polling. When it's close to 100%, it probably means that your server is bounded by CPU, and you should probably use other tools to drill down into why. It not necessarily may mean that the Scylla can't serve more. It could be also a configuration issue, for example, with one shard being overloaded by interrupts due to misconfiguration of networking. There are also memory utilization metrics. This diagram shows how Scylla memory is divided. We have memory which is allocated using standard allocator, and memory which is allocated with LSA. LSA stands for log structured allocator, and it's a compacting allocator which makes more efficient use of memory. We allocate mem tables and cache using this allocator. All other allocations are allocated using standard allocator. For reference, those are the metric names which allow you to see amount of memory for each of those parts. So why is it useful to look at those metrics? First, you can detect cases where you have pathological situation like cache getting shrunk down because of pressure from standard allocations. You can also look at the amount of dirty memory. When dirty memory piles up to the point where it reaches 50% of total memory, all incoming writes will start to get throttled. This is an example graph showing those metrics. The blue line marks total memory. Then we have LSA in yellow. In orange, we have cache. The red line is mem tables, and green line, standard allocations. So there's a couple of interesting things you can see on this graph. You can see that the red line has a sow pattern. This means that writes are incoming and increasing mem table sizes, and then they are flushed to disk, so it drops down. You can also see that the size of mem table memory doesn't build up, so this is keeping up with flushing mem tables. Another thing which we can see is that initially cache is populated. It occupies most of the memory, but then it starts to get shrunk down due to increased consumption of memory by standard allocations. This is something which shouldn't happen, and it may lead to bad performance due to us having a smaller cache and thus more misses. You can also see that when this drops down, cache populates itself again, and performance should be restored. So cache is important. So we have metrics for monitoring its activity. Those metrics count entries touched during various operations. We have metrics for hits and misses, merges, which count entries which were updated during memtable flashes, insertions, entries which were added either on miss or also during memtable flash, evictions, entries removed during on memory pressure, and removals, entries which got invalidated, for example, when the node loses ownership of a range. And this is an example graph of cache metrics during some load. On the top, the green line shows insertions. Blue line shows evictions. On the bottom, you see hits in green and misses in yellow. So we can see that initially we have a lot of misses, and hits are starting to pile up. Those misses are probably populating cache, so we can see that insertions are happening. There are no evictions, so cache probably wasn't full. The memory wasn't full, so it just populates itself. This translates to higher hit ratio. You can also see something disturbing happening here. Those spikes correlate with drops in hits, which probably also correlate with drop in performance. And those drops in hits are probably caused by cache getting shrunk down due to evictions. And this needs to be further investigated. So Scylla also has an IO scheduler, which ensures that operations belonging to different classes are served according to their priorities. Those requests are sent to different queues called IO queues, and we have a bunch of metrics for each such IO queue. We have, for example, a derive metric, which is incremented when it shows how many bytes were sent through this queue. It allows you to calculate bandwidth of given queue. There is a delay, which holds the queuing latency, the time it took for a request to go through the queue. There's queue length, which shows the current size of the queue. And finally, total operations, which is incremented whenever a request comes in. That allows you to calculate number of IO operations per second. All right, that's it.